Okay, this will be lecture 43 about embedded maximality by Harvey Friedman. Please.
Thank you. Okay, so I'm going back a little bit more on chapter three because I perfected the lead statements. It's very important to perfect them as much as possible. And I also perfected them given the way that I'm doing the finite forms to make sure that the finite form reads the same as the infinite form as closely as possible. So there's some expositional things going on here. I should finish this talk early, probably, which we're starting a little late because the chapter five isn't really filled with the proper details yet. But it's not going to be a long chapter. I'm going to limit it. All right. So, anyways, this is the constant table of contents for the book. Uh, and now, and these, as you can see, we're moving along here. We've got a version of two that has to be revisited. We have nothing on one, but we have a version of two. Chapter three is this thing that we're talking about and been talking about for a long time. This thing has been around for a long time without any change. There has to be some cosmetics in there to link it up with the same notation, but basically almost nothing I envision to be changed in this chapter. And then we're talking about this now. This is definitely, I want to get into this and this. So I guess next time I think I should finish up because I'm not, uh, I'm going to limit this chapter. Uh, I'm going to finish up this next time and maybe do a start on this. Um, that's my plan. I think I should, this might not even take the whole time. I think maybe I should be able to get into this. Okay, so we're making some progress. It's just that the real heavy chapters are three and four. Um, okay, so on the embedded maximality, there's a slight change. Let's see, I don't know if it shows in the table of contents or not. Let's see. That's all the same. Yeah, here it is. Um, So instead of calling it weak identity extension usability, you'll see what I mean. This is more natural. It's called half identity extension usability. And there's a thing called the half identity extension. And you'll see that later. And then this is all the same. This is all the same. These are the way I set this up was slightly perfected. It's not a big deal. Uh, But there is something here. You'll see that when I talk about the variance that I actually use to prove it. The field has this form. You show that without loss of generality, you can assume the field has this form or one other form, this form down here. Sorry, not far enough. Down here. See this form. It goes all the way to from 0 to 1. And this one, which goes from 0 and doesn't, it falls short. They both have length n. And so that there are really two cases. And I do this case and I just say what the minor modifications are to do this case. This is the way I set it up. This is a minor modification. It's basically the same thing. Then we apply this to the twos in here. This means dimension two, and this means cardinality of the field is two. And then we do the subtle cardinal combinatorics. Okay, so and then there is the half, the weaker one, half IEU, and it has the same uh, function situation. There's some little details that make it weaker. See, this half one is only at the roughly the level of Zermelo's set theory, whereas the full one, IEU, is at SRP. I don't have any I didn't really did any reversals yet here. All right. Um, okay, that's all the same. With the iterated exponentials, yeah, radar sure do. This W again, this is a mistake. H, H. Okay, this is all the same. All right, fine. So let me just jump into 3.6 because this has changed. The official statement, the lead statements of this subject have been changed many, many times. Oh, yeah, beyond. Okay, so here it is. Identity extension usability. So F is said to be limited if the endpoints are not both in the field. It's limited, it's unlimited if the endpoints are in the field. It's limited if not both, if limited if not both endpoints are in the field. Okay. The identity extension of a finite F is the extension of F by the identity on the rationals that are strictly above the field of F or strictly below. Oops, strictly below field F or strictly above field F. And of course, if field F is empty, it's just going to be the identity everywhere. Um, okay, so this is very natural. You have a function, you extend it by the identity higher and lower than the thing. You don't mess with the inside, just higher and lower. Okay, that's all that is. All right, so here is well, if F is limited, then the if F is limited, then the identity function is a proper extension of F, right? In fact, F is limited if and only if, I probably will change the, F is limited if and only if the identity extension is a proper extension. Uh, the following are equivalent. F is limited, the proper extension of F is a proper extension of the identity extension is a proper extension, and the identity extension has infinitely many fixed points. All three are equivalent. I'm going to state this that way. That's better. So they were all equivalent. All right. So here's the statement: the identity extension of any limited finite strictly increasing F is usable. That's what it is. That's the lead statement of the subject. The identity extension of any limited finite strictly increasing F is usable. And I use these little letters to mean partial maps from -1, 1 into -1, 1. That's a convention that's stated up front. That's what I mean by these little letters F, G, and H. The identity extension of any limited finite strictly increasing F is usable. Okay. And you got to have strictly increasing because that's necessary for any usability. That's been proved a long time ago. And also, you need to say F is limited because if F is unlimited, the proper extension is itself, but it may not be usable. See, it showed already from fin use that this function of cardinal, this function with whose field is cardinality 2, uh, this function is not usable. That follows from fin use. Okay, so we prove IEU, but we use all these large cardinals to do that, and it's reversed. All right, now what's the weak ones? The weak one is half identity extension usability. I like this situation setup much better. The half identity extension of finite F is the extension of F by the identity on the P that are strictly below the average, strictly below field of F -1/2, or strictly above field of F +1/2. these are the averages. So it's very simple. If they have the field is like this, then the half identity extension is going to go up some to the average of the max of the field and one. It's going to go like that and go down like this. You see, those are averages with -1 and averages with +1. It's a very simple idea. Okay, now here's the point. Singularities. Notice that in IEU, the identity extension of finite F will have a singularity at min F. I should write this, midfield F. Assuming the min of the field of F is uh, yeah, min of the field of F is less than F of the min of field of F. So, yeah. Okay, there's a singularity, right? Because it's all zero here, and then all of a sudden at the min of the field of F, it jumps. There's a singularity. That singularity is large cardinals. But in a half identity extension has no singularity because it's zero for a while, and then there's a gap, there's nothing there, undefined there, and then it does its stuff. And the same thing at the top. All right. So no half identity extension has any singularity. This causes a dramatic drop in strength. In fact, we prove HIEU, half identity extension, in ZC. Proof is highly unusual. It uses infinitely many cardinals. Okay, and then we have the obvious, the identity extension of any limited finite strictly increasing F with n element field is usable. We can also do this for the half one. The half identity extension of any limited finite strictly increasing F with n element field is usable. So we just put this in. I'm sorry, this is not right. This is what I mean. This is clumsy. The dimension is over here also. It's K usable. We now give two technical variants that we actually use. I mean, we actually use this, we sort of normalize things. It helps with the notation. It's nicer. I force them to be limited and things like that. So the identity extension of every strictly increasing F with field blah or blah, two different arithmetic progressions. One of them falls short, one of them goes to one, and the other falls short of one, is K usable. And the same thing over here, the half identity extension of every strictly increasing F with this field or this field is K usable, where K and N are fixed. Thus, IEU and HIEU are the lead statements of embedded maximality. The calibrated lead statements of embedded maximality are IEU and HIEU. Okay. The technical variants we actually use. Yeah. When we it's just explicitly stating what the field is. Um, okay, and then we have the equivalence between variants as before, which is pretty easy to prove. Easy to prove. Some of it's completely trivial. The only one that's slightly non-trivial is the reverse, is the contrapositive of this one and the contrapositive of this one. You have to prove that you can normalize things, but that's pretty straightforward. All right. Now, chapter five. Let's move to chapter five. So that's what chapter three is. I'm very close to releasing it, pretty close. I just need to sit down for one whole day without any interruptions and just go through it line by line. Uh, Day two, maybe. So maybe I think I can do that over the weekend, probably. Now I don't really think there's going to be any more change in the lead statements. I think they're very polished now. All right. Now, chapter five has just got six sections. I don't think I want to be more ambitious. That'll be part of future investigations. Uh, in other words, I'm not calibrating this to K usable, and I'm not doing all that calibration work that I did for chapter three. Uh, just leave it this way. Okay, so there's a notion of okay, I picked a way that I've known for some time that'll work, and I finally come around to thinking that this is probably the most straightforward way, and I definitely want to have a finite form. I like it somewhat better than the form where you actually have a computer science algorithm. But that's another idea which I might do, a little mission creep. Maybe I'll have a section here, um, algorithmic formulation, which will be extremely similar and probably require no new ideas in the proof, but a restatement, algorithmic restatement of this. I probably will do that. A non-deterministic algorithmic restatement of exactly this. That's a good idea. That should be part of chapter five. Algorithmic restatement. All right. And that should be covered next week. All right. So okay, so I have a notion of staggered maximal arc chain. Uh, okay, so the key definition we need is S sharp. S sharp is the least cube containing S. Maybe I should. People feel more comfortable when you do this. Maybe I'll do this. Okay, it's just the least cube containing the set. All right. So let R be a relation on -1 to the K, a staggered E maximal arc chain, a staggered E maximal arc chain. So I got to say, and yeah, this is. Okay, staggered E maximal arc chain is a sequence S1 through Sn of finite arc chains. Each one is a finite arc chain where no SI is a proper subset of any arc chain contained in SI union E union SI -1 sharp. Okay. Well, now, what is a maximal arc chain? Is an S, if I were to say something much stronger, that SI is a maximal chain, I'd be saying um, two there. Uh, if I were to say that it was a maximal arc chain, I would be saying no. I say that SI is not a proper subset of any arc chain. Here I'm saying something weaker. SI is not a proper subset of any arc chain contained in some bigger stuff. Well, it's staggered, contained in the sharp of the previous S and also E. So the idea here is that I don't say that SI is maximal. I actually say, I don't say that it's not, it may be a subset of a bigger chain, but it's not a subset of a bigger chain that's contained in some stuff. So you get used to this, makes sense. Then there's a set E that you start with that sort of gets things going. E is not part of the system. Here's the system. Now, actually, have I done this right? I have not. This should be, this is under inclusion. Yes, this is under inclusion. Yes, and it's important, really important. Staggered R maximal arc chain is a sequence S1. It's a tower. So I'm now going to say tower, I guess. There we are. Where no SI is a proper subset of any arc chain contained in here. Okay. I probably should say something about the robustness of this. If I change this a little bit to, I replaced this SI with SN, but I kept this down here, I minus one. And I made this N, I would have a slightly stronger statement, but that turns out to be equivalent. Okay, so there's probably some things I should add to explanatory things about this. All right, now F is usable stag if and only if for all finite E in every order invariant relation on here, every order invariant relation has an F embedded E staggered maximal arc chain of every finite length. Okay, that's what it means to be usable. And so we have the F is usable implies F is usable stag, and F is usable stag implies F is usable. I see pretty clearly I need to have F. We need to know something about F. Almost identity is a good notion. An almost identity function is a function which is the whose set of non-fixed points in its domain, the set of points that are moved is finite. And all of these functions that I reversed, all of the functions whose usability is so strong are almost identities. Okay, so we have usability implies usability stag. And the other direction is that usability stag implies usability. And that's the more interesting part. This is sort of obvious, except you do need F as almost identity. Here, I haven't really written this up yet. I mean, this is about to be written up, and it should be pretty straightforward. I think I'll probably use directly compactness theorem rather than non-standard models. I might use non-standard models if the compactness theorem has any complications. But the idea is you have these longer and longer maximal chains. Uh, there's some theory that every finite subset of which is consistent. So you can do this. And putting this all together, you show that IEU fin. Oh, so I have to tell you what IEU fin is. So where is that? Did I erase that? Oh darn. Okay. That is like this. Yeah, IEU fin. Okay, so IEU, no, it's not called IEU fin, it's called IEU stag. So this is all screwed up a little bit here. Stag. Okay, and what it is, let's go take this statement, this IEU statement for here, right? This is the old thing from the chapter 3. And now this is going to be, so let's make another copy of this. Okay, so this is going to be stag. Staggered identity extension usability. The identity extension of any limited, okay, no. Yeah, the identity extension of any limited finite strictly increasing F is usable stag. That's it. The identity extension of any limited finite strictly increasing F is usable stag. And usable stag can be matched up side by side with usable. So one talks about uh, maximality, and the other has this limited form of maximality. Yeah. Okay. So I think that's the way I'm going to leave it. Except that I will put in the computer science version, which is nothing more than, which is very similar to trying to build that tower. Um, I might change it to a towered E maximal R chain. A towered. Yeah, I could, instead of staggered, I might use towered instead, because it's very important that these be under inclusion. A towered, and then yeah, let me do that. All right. Use a little tower. F embedded. Towered. Yeah, I might play with the words a little bit here. Tower. Yeah. Tower, tower, tower. There we are. This does not require any additional infinite talk. It's just taking the maximal chain stuff and just making it a towered maximal chain. So this is the way I'm going to do it. Plus, I'm going to put in, I just do a routine computerized version where you have a non-deterministic algorithm. All right, now there is something else though. I this is mission creep, and I think I may do this. Let's go back to where this was here. Not here, just where we were. Here we are. Here, the tower maximal chain. When n is equal to 3, I think it's that. When n is equal to 3, we're talking about it might be called a 3 tower or a triple tower, maybe. When n is equal to 3, I think that this is already going to give me a strong enough notion that we have con SRP, that it's independent, it's large cardinals. I have a feeling that this is the case. I've done things like this before. Um, if F is usable 3 tower, then F is usable. 2 tower, I'm a little suspicious of. I have to look at that again, but I think that I never really understood that. That would be a double tower. A triple tower is length 3. So one open question might be if I have this with double tower, is it independent? I don't know. I have to take a hard look at that. Um, so this is pretty clean. I think the idea of a triple tower should be pursued carefully. I think that that should be that should also be con SRP. I'm pretty sure I know how to do this kind of thing. I've done it before. All right. I think that I think that's all I want to say today. That's all I really can say today. Um, and maybe you'll have some questions for me. All right, I think I'm done.